Assalamualaikum and salam sejahtera. So for today, let's continue our lecture by chapter 7. So the topic is gravitation, and there are three subtopics, starting by 7.1, which is gravitational force and field strength, 7.2, gravitational potential energy, and 7.3, which is satellite motion in a circular. Okay, so we are discussing about gravitation. So let's start by the first subtopic, which is 7.1, which is under gravitational force and field strength. So as usual, we just start by the definition. Okay, for the first subtopic, students should be able to state and use the Newton's law of gravitation, also define and use gravitational field strength. Okay, so what is the definition of gravitation? So according to Newton's law of gravitation, the statement is the magnitude of an attractive force between 2 point masses is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. Alright, so there are two different factors. The first one is the force is directly proportional to the product of masses. Okay, and the second point is inversely proportional to the square of distance. So in this case, by having two different vectors, the first one is directly proportional. So this is the first factor. F and the product of masses, they are directly proportional. And then the second factor is the force also inversely proportional to the square of the distance. So this is the second factor. So by having these two factors, we just combine it and then you will get this. Okay. The force now is directly proportional to m over r squared. Okay, again, directly proportional to the product of masses and inversely proportional to the square of the distance. So mathematically, you will get the equation of Fg equals to gmm over r squared. Okay, so what is that actually? Okay, so let's go continue by the equation. Alright, so according to the equation given just now, alright, so Fg is the gravitational force equals to gmm over r squared. Okay, so this is the equation. Fg equals to gmm over r squared. So what is gmm and r squared? Okay, we just refer to the notes given. So Fg is our gravitational force. M and m here representing the masses of particles, which is particle 1 and particle 2. Okay, remember, to have any attraction, there must be two different bodies, isn't it? So this is the mass of each body, which is body 1 and body 2. And r is the distance between particle 1 and particle 2. So r actually is the separation between them. Alright, so what is g here? Okay, mathematically, you will get this equation. So g is a constant. We call it as universal gravitational constant, where the values is fixed already, equals to 6.67 times 10 to the power of negative 11 Newton meter squared per kilogram squared. Okay, so this is the example given by having two different bodies now, which is M1 and M2. So two particles given, where the mass of particle 1 is M1 and the mass of particle 2 is M2. So according to the gravitation principle, which is introduced by Mr. Newton's before, so these two bodies, they will attract each other. So the force exerted on them is F12 and F21. They will attract each other, caused by gravity. Alright, so what does it mean by F12 and F21? Okay, F12 is the force exerted on the first body caused by the second body. The force exerted on the first body caused by the second body. Still the same for F21. F21, the force exerted on the second body by the first body. It's quite simple. So on by. Okay, on by. All right. And remember, for these two forces, they are equal in magnitude. Okay, but opposite in direction. That is why the magnitude of F21 equals to the magnitude of F12, which is equals to our Fg, which is gravitational force. Why they are equal here? Because we are using the same equation, G m1 m2 over r squared. G just a constant, r is the separation between them, m1 and m2 is the mass of each particle, so they are the same in magnitude. Alright, so remember, equal in magnitude but opposite in direction, for this example. Alright, next we just continue by the gravitational field strength. Okay, this is Fg, gravitational force. So now we just continue by the gravitational field strength. The symbol is Ag. So what is Ag actually? Alright, so Ag we name it as gravitational field strength. So gravitational field strength is a region of space surrounding a body that has the properties of mass, where the attractive force is experienced if a test mass placed in the region. Okay, it's quite simple. By locating any particle in that region, the force exerted on it, the force we call it as gravitational force. That one is our attractive force actually. Alright, so field lines are used to show gravitational field around an object with mass. So in this case, okay, to show the gravitational field strength, okay, we are using a lines. So the lines now representing our gravitational field around the object. For example, like this. There are so many lines in it. So the lines now representing our gravitational field strength. For spherical objects such as the Earth, the field is radial as shown below and towards the center of the object. Alright, so for any spherical object, our gravitational field strength just surrounding the object, and remember it must directed towards the object. For example, for our planet Earth, the gravitational field strength just directed towards the planet here. Alright, so for this line, remember the field lines indicate two things, which is the arrow. The arrow here now representing the direction of the field, which is towards the center of the planet here. And then the spacing between lines representing the strength of the field. Alright, so according to this situation, the line here is quite closer to each other, isn't it, compared to this part. Means that the strength of Ag here is stronger. Closer line giving you stronger gravitational field strength. Okay. Okay, next, what is the equation of Ag or gravitational field strength? Okay, the equation is gravitational field strength is defined as the gravitational force per unit mass of a body, test mass placed at a point. Okay, the first keyword given here is gravitational force. Okay, per unit mass. So A equals to gravitational force per unit mass. So this is the equation. Ag equals to Fg over m. So again, Ag now representing the gravitational field strength, Fg representing the gravitational force, and m is the mass of the object. Alright, so in this case, it is also known as gravitational acceleration or free fall acceleration. And again, acceleration is under vector quantity. The SI unit of the gravitational field strength is Newton per kilogram. and gravitational acceleration is meter per second squared. Okay, all right, so in this case, the symbol of AG still equals to G actually. Some books take it as AG. Some book take it as G. So they are equal actually. Alright, so we call it as gravitational acceleration or free fall acceleration. Okay, so by knowing AG, we may calculate the weight of the object. Okay, because weight now equals to Fg. So in this case, Fg equals to Gm over r squared multiplied by m, or Fg is Gmm over r squared. Alright, so we just separate this equation to be Gm over r squared multiplied by m. So Gm over r squared now representing G. Then the equation still equals to mg. So in this case, remember Ag and G, they are equal. Some book take it as G. Some book take it as Ag. So they are equal actually. Alright, so by knowing Ag, we may calculate the weight of the object, which is equals to mg. Alright, so again, capital M here representing the mass of the planet. Okay, m is the mass of the object. Alright, r is the radius of the earth because the object now just located on the surface. The separation between the object and the planet. Alright, and then g is the acceleration due to gravity. Okay, on the earth's surface. Why? Because the object just located on the earth's surface here. Okay, so by knowing G or Ag, we may calculate weight of the object. Okay, how do we derive the equation of gravitational field strength? Okay, so remember the direction of gravitational field strength still the same as the direction of gravitational force. So direction of Ag still equals to the direction of Fg. And direction should be the same. Alright, so the equation for the gravitational field strength at points is given by, alright, so let's start by the equation. The main equation of Ag is Fg over m. Alright, and as we know, Fg, the force equals to Gmm over r squared. So we just substitute Fg into this equation, and then you will get this. Alright, so what do we have now? Ag equals to Gmm over mr squared. So m and m cancelling each other, giving you Gm over r squared. Okay, so this is the main equation of Ag. Alright, Ag equals to Gm over r squared. Again, G just a constant, m is the mass of the planet, and r is the separation between the object and the planet. And remember, r should start from the center of the planet. It's not from the surface, center of the planet. For example, for this case, okay, r should start from the center. Should be here. So this is r actually. R measured starting from the center of the planet to the object position. Alright, this is r. Okay, and then how about the value of Ag? Is it the same below the surface of the planet, on the surface, and above the surface? Okay, let's continue by that part. Okay, alright, so what do we have here? So there are three different positions given, okay, which is, okay, let me show you first. The area below the surface first, and then on the surface, and the third one above the surface. So what happened to AG? Oh, it's not so clear. I think I need to change the color lah. Better, Wait, I need to change the color. Okay, this is the first one. The first one is below the Earth's surface. Second, using blue lah. Above the Earth's surface. And next, sorry, before that is not above, on the Earth's surface, and now above the Earth's surface. 3 different positions. Okay, again, below the Earth's surface, on the Earth's surface, and above the Earth's surface. So what is the value of AG? Are they equal or different? Okay, now let's start by the first part, which is below the Earth's surface. This is the Earth's surface. So below the surface, what is the value of AG? All right. So the equation of density is mass over volume. All right. By rearrange the equation, you will get mass equals to rho V. Okay. So M equals to rho V. This is V. This is the volume for any spherical object. 4/3 pi r cube. Okay, from this, the equation of AG equals to GM over R squared. So we just substitute this M into this equation. Then you will get this. Alright. So what do we get now? G over R squared, 4/3 pi r cube rho. So in this case, R squared and R cube, okay, they are cancelling each other, giving you R only. So what do we have now? The question is AG equals to 4/3 G pi rho R, where AG and R, they are directly proportional. So here, AG and R, they are directly proportional. That is why the graph is linear here. And what do we have? Just a straight line graph. Because AG and R, they are directly proportional. So this is the graph of AG against R. Okay. So below the Earth's surface, AG and R, they are directly proportional. Okay, on the surface, what happened? On the surface, R equals to R of Earth. Okay, because the object just located here, the separation between object and the center of the planet is R, isn't it? Equals to R of the Earth. So, means that the value of AG on the Earth's surface is constant. Because G just a constant, M is mass of the planet, which is Earth, and R is R of Earth, also constant. So constant, constant, and constant, giving you one value which is constant. So on the Earth's surface, G always equals to 9.81 meter per second squared. Okay, above the surface. So above the surface, the values now is 9.81, nearly to be 10 lah. Here, fixed already. Alright, and then above the surface, what happened? Okay, above the surface, we just refer to the equation of AG equals to GM over R squared here. Okay, so in this case, AG and R squared, they are inversely proportional. So AG and R squared, they are inversely proportional. For any graph which is AG against R, it must be in curve to be like this. Alright, so again, starting from the center of the planet, AG and R just directly proportional. On the surface, AG just constant, which is 9.81. Above the surface, AG and R squared, they are inversely proportional, giving you this curve. Alright, so